Folks, I'm happy to introduce our speaker today. It's Pedro Moreno. So Pedro comes to us from Google now. The way I met him at Google is one fine day I was visiting. I had no idea he was there. I had gone to meet some other people in Google. I was at the cafeteria, and in walks a familiar figure. And for about 30 seconds, it didn't even register to me that I wasn't expecting to see him there because, of course, he's a familiar face in the speech and language community. And then suddenly struck me. I asked him what he was doing, and of course he had moved to Google, just like a whole bunch of other people we know. But before Google, he did some really remarkable work at HP, which was it already DEC or was it HP?
It was DEC, then it was bought by Compaq.
Okay, so basically they have something called the SpeechBot, which was sort of the first large audio indexing tool that was out there on the web, and they did some really nice work for indexing broadcast audio and a lot of other things, so you could really do large-scale speech search. Before that, of course, Pedro was at CMU, where he worked with Rich Stern, and he was one of the people who's who made Rich Stern famous. So I won't say more about that. He finished in '96, and he's been in industry since then. And today he's going to talk to us not about speech, but about music.
Thank you. So the way I like to think of this talk is how can you use the speech hammer to do something else? This is really a side project. It's not like we do this or this is used in our Google infrastructure. This started 2 summers ago, no, actually 3 now, with a summer intern, Eugene Weinstein, who is a PhD student of Mary R. Mori at NYU. And I was curious about fingerprinting. I have been reading about it, and it struck me that a lot of the machinery we have in speech recognition could be possibly used. So this talk basically tells you about this. And it's really Eugene's work. I have been supervising, whatever that means. So I might not know all the answers. I'll do my best. Before that, I wanted to tell you just a little bit about the speech team, because this is a speech research lab. The speech team in Google started, actually when I joined, there was not a speech team. And I guess my secret hope was that, come on, this is obvious. Google has to do a speech. And sure enough, it happened. It took a couple of years, I think, a year and a half. So this started in 2005. And of course, the question was, what are we going to do? Do we buy or license? And in Google, there is this belief that we should write our own software. So it was decided to build our own engine, our own speech team. So right now, the team has probably 30 people between engineers and researchers. The manager is Mike Cohen, who was one of the founders of Nuance, the first Nuance, not the current one. It's evenly split between New York and Mountain View. Traditionally, most of the core speech recognition algorithms, the training, the decoding, has been done in New York, and in Mountain View they have been focusing mostly on the applications. Recently things are changing. They're working also in Mountain View more on the algorithms, and we are in New York working more on the applications. And we have an active summer intern program, so I encourage you to apply. Carolina visited us last summer, and I think the experience was good for both of us, so please apply. I was telling in one quick meeting with the students that Google is really, at least the speech team is very engineering oriented. So we really are pushing to get the speech products out there, often at the price of not thinking too much about the research, because we are pushing very hard to get things out. So in these few years, we have these speech products out. One is Goog 411. It's still there. You can try. This is basically search of businesses and things like that. There is Google Voice Search, which I believe started last summer. And the idea here is that you can query Google for the same thing you could query typing. And then in the audio indexing side, we have, in Google Labs, there is a political candidate search, where you can search for things the candidates for the last elections said. The Goog 411, just to go very briefly through it, is what I described. You can basically search for location-specific queries. You engage in a dialogue where you say the city, the state, and then what you're looking for. And then Google will query Google Maps. It will tell you a bunch of candidates. It has to read them. And then you say number one, and you can actually say, connect me, and we will do the connection for you, we will pay for the call. So I cannot give you statistics about the traffic, but it's pretty big, keeps growing. The first generation of this product was basically around the concept of building a language model per city and per state, and the idea was to query the Google search databases, build language models related to particular queries, to particular cities and states, and then have a lot of language models. That actually generated a lot of problems because we have like 3,000 or 4,000, or actually 30,000 language models that you had to bring into the recognizer. Things have changed a little bit. Now we do more things in a more hierarchical way. And a lot of experiments have been going on in this system. It keeps, as I said, it keeps growing, although we don't put so much emphasis on that. The emphasis now is on voice search, mostly because there is no telephone infrastructure. In voice search, the audio goes through the data channel in your smartphone. And the interaction is freer. You can say anything you want. Anything you can type into Google, you can say. I find often that long queries work very well, like who discovered America? So this is also growing. It's doing pretty well. We're now looking at doing the same in different languages. Here, the system, we bootstrap this using GOOG 411 acoustic models. So even though there is a little bit of mismatch in the acoustics, it was a pretty good model to start. And here, we actually use a single language model. It's a massive language model, but it seems to work better. Cyprian actually has been helping a lot with this. And he has been using a lot of the translation infrastructure to train massive language models quickly in parallel. One of the issues we had to deal with was actually this problem of, because the language model is trained on queries, we basically look at what people actually type on Google search, and based on that, we try to build a language model. But as you can imagine, what people type is not the same as what people say, so you need to do this ambiguation. So there has been some work into that. Carolina actually worked on that last summer. You guys sent a paper to ICASS, right? Yeah. So hopefully we'll be there. And basically the whole thing is running. There is a lot of tuning that is, engineering issues, latency. Right now, it's available for most English languages. Of course, if you're Canadian or British, your accent will be an issue, so we're working on that. But things are working well. The other side of the project, yes?
With GOOG 411, you say direct thing, right? You say what city, state, all of that is. But then later on you said it's free voice.
So I think there is a second generation where they have been looking at making it more flexible, where you can say things in a single shot, like Chinese restaurants in Palo Alto, California. That's the second generation.
So what kind of queries do you get? I mean, do people still behave like the old way? Will they still use Chinese food, Baltimore? Or will they go, I would like to know about Chinese restaurants in Baltimore or near?
To be honest, I don't know. I don't think this has been publicized. Okay. So a lot of these things in Google are released as kind of Eastern eggs. We don't tell people, and we see if we... I mean, it's based on observations. The reason this was done is because they observed that a lot of people had that way of interacting, but I guess I don't know the answer exactly. So the other side of the project, in terms of volume, in applications, has been indexing, right? And that was actually my motivation for joining Google, to work in audio indexing. So a lot of the work has been really based on building an infrastructure that can process millions of videos currently stored in, say, YouTube, and process them, transcribe them. We need systems, for example, to identify. So the pipeline we have for audio indexing identifies the language. If it is not English, we reject it. We have music detectors, all these things, because if you look at things like YouTube, let's face it, 80% of it is junk. I mean, from the point of view of content, okay? It's a teenager in his skateboard breaking his teeth. So there's not much you can do with speech indexing with that. But there is content in which you can. So because the content in YouTube is humongous, a lot of it is junk, we decided to start with a problem where we felt we could bring value, and that was the elections search. So this is still there. I imagine that over time we will add more channels, but again, this is mostly experimental. It's in our labs. And here you can see, I mean, the system it's there. You can just connect and see how it works. And of course, again, being Google with this culture of building everything ourselves, we decided that, and of course we had David talking in the team, we decided that we wanted to have our own text-to-speech engine, and it's called Goose. And it's basically based on the voice of one Googler. And this is what serves actually the traffic in Goog 411. And they are now doing localizations of the synthesizer for English with an Indian accent, because there is a version of Goog 411 actually in India. It's a little bit different from the one we have here. And the interesting thing is that the guys in YouTube decided to actually wrap the TTS engine and allow people to speak the comments they put in the video. So that's a kind of a cute application of the TTS. So anyway, at least I gave you a little bit of an overview. Yes?
Just a quick question. In audio indexing,
Yeah.
you've got speech on one side. On voice search, you've got speech on the other side, on the query side.
The query side is text.
On voice search?
Oh no, voice search is speech. Yeah.
You're doing it both sides. Do you have lattices on both sides in each case, or do you have one best?
So in voice search, you speak and you search web pages. So it's text. So it's a speak, retrieve web pages.
I understand. Are you using the one best decoding?
We use the
speech?
one best, yeah.
Okay. And for audio indexing, are you using one best of the election coverage before you search?
Yes, also. Although it's the difference is that the voice search system is a single-step decode, because we don't want to spend time doing adaptation and multiple passes. While in the indexing system, we do a multi-pass. So in some intermediate steps, we might dump a lattice and then rescore it with a more detailed language model. But at the end, the index is based on one base.
The index is like text, right?
Yeah.
And the denormalization, I'm sorry, text normalization, I'm missing your terminology, on voice search,
Yes.
is also one best. So if somebody says Xbox 368 megabytes, 368.
Well,
is not
Carolina can
approximately
answer for you because she did it.
Oh.
It's transducer based, right?
Yeah, it's a transducer. We rescore the transducer with a language model and use the best.
Yeah, so you do one
Okay,
base.
so it's again one best.
It's a one base, yeah. Yeah. Okay, so I told you a little bit about the speech team, and now this kind of a side project, which I think is cute in the sense that it shows you, hey, whatever you learn here in speech recognition, you can apply to other areas, like music fingerprinting. So let me just get into it. So the scenario you have in music identification is that you have a collection of songs, 20,000 songs, whatever, millions of songs. And I give you a few seconds and a snippet. And I want you to tell me what song this snippet corresponds to. And I'm talking about the same recording, okay? It's not me humming or it's not me playing the guitar. It's the same recording, modulo noise effects and things like that. So when you think about the problem this way, and you come from the speech background, it sounds interesting, like, okay, I can do feature extraction and transform the song into a sequence of features. A song is like an utterance, and there is some grammar there, right? So maybe if I can come up with a transcription of this song into, let's call it words, music words, then I can use language models, right? Will it work? So what kind of problems we're going to face? So that was the motivation, and that was what I wanted to try. So most of the work we were aware to deal with fingerprinting are really based on some form of a spectral feature extraction. Often they focus on spectral peaks because they're more resistant to background noises, which hopefully they will be lower in the spectra. And then some sort of hashing scheme. Things like local sensitive hashing or varieties. There is a little bit of tolerance to noise, but most of the schemes are like that. A lot of that work has been done at Philips. There's a lot of patents, and there are a lot of commercial systems that work like that, and they work very well. There was some previous work where they tried to apply hidden Markov models. This was done by Batlle. This is Universidad Pompeu Fabra in Barcelona. But that was the closest we could find, but it wasn't the same. So basically, we approached this from the point of view of a speech. And in what I described you, the main problem you have is that you have a collection of songs and I don't have a transcription, right? What I described at the beginning, if I have a transcription, maybe I could squeeze this into a speech problem, in a speech approach. So this is how we started this work. We started with a small collection, only 15,000 songs. This is what actually, the reason we didn't get more songs is legal issues. And actually nobody we knew had more than 15,000 songs. So this is the most we could get. And as I described, we go the traditional way you would follow in a speech. We use MFCC features. There is evidence that MFCC features are okay for music processing. There is previous work in detecting, for example, the relevant part, the theme of a song. They did it using MFCC features. There is work also where they try to identify the style of the music, whether it's rock or not, and they also use MFCC features. Yes?
So are you using songs and music interchangeably? Songs and music, is it?
Oh, you mean if there is vocals or?
Yes.
We don't care, yeah.
You don't care?
We don't care, yeah. Yeah. Whatever the collection has. It has classic, it has rock.
So songs is really music?
Yeah, yeah. So the main issue is how do we go about building a vocabulary of music units so that we can go through this transformation from song into sequence of symbols. So this is what we really need to start this process, right? So let me just get into details here. So the simple idea we use, and actually this has been done by many people. One of the people we knew was Michiel Bakiani, working at BU with Mari Astendorf. They had a similar problem trying to learn phonetic units in speech recognition. So we use a similar approach, which is basically build a system that detects a spectral change in a song. You can easily do that. There are many ways. One simple way is you use a running window. On the left of the window, you feed a single Gaussian model. On the right, you feed another Gaussian model, and then you compute some sort of distance between the Gaussians, for example, KL divergence. And whenever you see big transitions, you hypothesize a break. So that gives you a pre-segmentation of the song into pseudo-stationary units. Then you basically run k-means on this collection of units, and that's going to give you, let's say you settle this for 1,000, what we are going to call music phonemes or music fonts. And now from this, let's say 1,000 music fonts, I have my set of units, and I can actually train a Gaussian mixture model to each of these units. So how do you do that? Well, the first thing you need is to produce a transcription for each song, okay? So what you can do is, now that I have my vocabulary of units, I create a language model. Basically, it's not a language model. It allows any possible transition. And I decode each of the songs with this initial acoustic model and this empty language model, right? And that is going to give me a sequence, the one best, a sequence of symbols or music phonemes per song. Once I have transcriptions for it,
1,000, 1,000?
We experimented with 1,000, 2,000, so let's say 1,000, yes.
So assuming that this segment has its own length, how do you the k-means? What distance do you use?
So the distance is based, for the k-means is based on the sufficient statistics of each of the segments. It's based on the Gaussian mixture. So like you would do in tree clustering or things like that. Again, very well known.
If you have a very sharp segment, you still
Yeah. Yeah, it's just for K. No, so the mixture, at the beginning, the very first model you have has a single Gaussian, okay? So it's a very simple model. You decode and do Viterbi with no language model, and based on that, I guess I get a sequence of symbols. Probably it's going to be bad, but at least I have a transcription to start with. So now each of my 15 songs has a transcription. Now, once I have a transcription, I can do regular acoustic model training, right? So what I'm going to do is I'm going to freeze the transcription and relearn the acoustic models, okay? The Gaussians of these 1,024 symbols or music phonemes. So I'm going to refine my acoustic models. Once I have these acoustic models, I'm going to freeze them, and I'm going to decode again, okay? I'm going to do Viterbi decoding with no language model, just allowing anything, and that's going to give me a new transcription. And I'm going to iterate this process. And
in principle, is it possible that in the transcription, you're changing phonemes every whatever 10 milliseconds. Every frame could in principle end up being a separate phoneme, right?
Yes.
But you don't control for it, you just hope that the consecutive frames will be similar enough that this
Yes.
won't happen.
Yes. So in fact, we went back and forth. Our phoneme model is a single state. You know, we could have limited to 3 states. We just went for the simplest thing. And in order to track convergence, you know, is this thing converging or not? What we do is we compare the edit distance between the transcriptions that the system hypothesized for the 15,000 songs after each iteration. And what you see is that things are converging. The transcription is getting stable. It's not changing too much.
Is this the subsequent iterations?
Yeah. So eventually, it almost, you know, there is always changes, but very small. So eventually, you settle into something that is more or less stationary. Now we have reached a very comfortable point from the point of view of speech recognition. I have a transcription for each song. So now my problem is a problem of, it's more similar to speech, right? I'm going to be given a snippet of audio, and I have to find, of all these 15,000, which one matches the best, right? Because this is identification. I'm going to be given, I'll talk about detection later. And in identification, I know the snippet of audio matches one of my 15,000 songs. I don't know which one. So our first idea was very naive, was, well, let's build an engram. And we rapidly ran into all sorts of problems. The language model was humongous. It blew up in size. You needed very, very large engrams. And I think this is where Meriar had this brilliant intuition, and I'll tell you about it in a second. So just to recap, the idea is really to use finite state transducers, which is actually the core of our speech recognizer. Our recognizer is based on the OpenFST library, where we do the representation of the knowledge sources, the C transducer, the lexicon, the language model, all through transducers and automata and composition to produce a compact network. So, you know, they're very popular in speech, and that was a good motivation. And at this stage, our song collection is represented by strings, so it looks like a natural problem. Now, the mapping of the only issue is I have a snippet of audio, and I have to find the match within the transcription, right? So effectively, what you're looking is, this is what they call in automata theory a factor. You basically want to match imagine I give you this snippet of audio represented as a substring, 5 or 10 or 20 music phonemes. You basically have to find a substring match within this collection, okay? So let's look at this a little bit more carefully. So imagine that I build a transducer like that. In this case, it has only 3 songs, okay? The input symbols are the music phonemes. For example, the upper branch has music phone 72, followed by music phone 240, music phone 2, and the output symbol is the Beatles' Let It Be, right? And so forth and so on. So how do I match a substring to this? So let me go a little bit more in detail. Yeah?
How do you get that transcription, the Beatles Let It Be?
So each song, in this iterative process where we freeze the acoustic model and we learn the transcription, then we freeze the transcription, relearn the acoustic model.
The transcription is just MP72 followed by MP22. Yeah.
It's a linear, it's a string, right? It's a sequence of music phonemes. It's a one best, that's it. You could possibly expand it to do lattices or who knows what. But every song has been translated into, it's like a speech, right? An utterance has been translated into a sequence of words. Same story.
Also, you have a mapping from those MP72 to some word, some like transcription.
No.
Are you asking about the place where it says Beatles Let It Be?
Yeah.
That's supervised. That's the name.
Yeah, I know my collection.
That's just a name. Okay.
Yeah, I mean, yeah.
It's not transcribing anything from the audio.
Yeah, hopefully when I have my 15,000 songs, I know the song title for each song. If not, at least I could tell you it is song 24 out of your 15,000. Whatever, if that is useful or not, it's another story. So yeah. So the only problem of doing that is that this is only going to match an exact song, right? If you give me the same song, I can tell you whether I can do composition and I can tell you whether I match or not. But this doesn't work for snippets, okay? So you need to do something a little bit smarter. So what you can do is do the following. You could do the first thing you could do is allow a transition from the initial state to each state, okay? So this would actually transform my transducer into a suffix automaton or a suffix transducer, because it would allow me to model each substring, okay, from the beginning, from any state to the end. That's still not good enough, because my snippet might not, this basically would allow me to match any part of the song that goes from any point in time up to the end. So if I'm presented a snippet that starts at time 5 seconds and stops at 20, this wouldn't match. So the next thing you can do is declare it a state final, okay? So now this transducer, when it's modified this way, allow any possible factor, any substring, starting anywhere within the song and anywhere, and ending anywhere within the song, right? So this transducer will allow me to match a snippet. So, and of course, if you want to get a network that is efficient, you need to determinize and minimize. Now, if you do it this way, you still run into explosion problems in the memory space. So you need to still do a couple of tricks. And actually, if you minimize and determinize, you will get a transducer like this, okay? But the problem of this is that this still doesn't identify songs. So basically, we have transformed the transducer into an automaton. Okay, we have removed the output symbols. So the only thing we now tell you is whether things match or not. Because if we keep the output symbols, the whole thing explodes. When you go through determinization and minimization, the whole thing is humongous. So we can do this trick of basically saying, okay, let me turn this into an acceptor, and now I can tell you whether things match or not. Okay, the transducer is smaller, but it doesn't do what I want. I want it to tell me what is the song that matches, not whether it matches the graph. So you need to do another trick, which I think is very cute. And this is a trick I think is well known for automata experts. The idea is that in this song graph that I have at the bottom, I'm going to replace the output label, for example, Beatles, Let It Be, or Madonna, Ray of Light, by a number. Okay, number 1, the first branch is number 1, the second branch is number 2, the third branch is number 3, so forth and so on, up until 15,000. Okay? Then I basically transform this into an acceptor, a weighted acceptor, in a semi-ring which is additive, where you can just add the weights. Okay? So then I transform this into an acceptor, I produce the factor automaton, I minimize, determinize, and the end result of all this is that this factor acceptor preserves the weights. So this is the cute thing. The weight of a particular song has been preserved. So if you match any substring within a song, it will be guaranteed that it has when you compute the weight of going through that path, that weight corresponds to the song label. And when you do this transformation from transducer to automata, where the weight identifies the song, the whole process of minimization and determinization is smaller. Your transducer is much smaller and it happens. Yes?
Now, the degree of minimization you'll be able to get depends on how you assign those song IDs, right?
I'm not sure in what sense. I mean, your IDs, you do all this, you do weight pushing. These are integers. It's a semi-ring, additive numbers.
Yeah, but you may not be able to get as much structure sharing depending on how you do the weight. So the traditional example of this,
sure.
Depending on how you assign the numbers.
Yes,
the traditional example of this is if you're trying to do perfect hashing of a set of strings, if you assign 0 to the one that's first alphabetically and 1 to the one that's next alphabetically,
yes, that makes a difference.
Then it works out well. But if you assign them randomly, you wouldn't get as much minimization.
Yeah, that is true. That would make a difference.
So how do you assign the numbers?
We just go 0 to n, and that seems to work. This is something we didn't explore.
It's essentially 0 to n in what order? Based on the
Nothing. There is no.
a DFS and the unminimized machine, maybe.
I don't think so. I think we just assign, randomly. First song, number 1. Second song, number 2.
I bet you can do better, actually.
Yeah, probably, because we haven't. This is a total random assignment, and it worked. So it is true. There might be an assignment of numbers that gives you a smaller transducer.
Talk to Mike Riley, because I think he's working on a similar problem.
It's possible. Yeah. So this is a cute example of how you have basically transformed a problem of fingerprinting into a problem of search, where we have used acoustic models to model the acoustics of songs. We have induced a vocabulary of phonemes, and then we are doing search using automata operations with this extra trick, which, as Jason tells us, is well known in the community of automata people, not me. So I think it's cute how for each of the steps we have been applying things you are familiar with in the speech community. Now the question is, does this work or not? One thing is, what is the size of the transducer? So in this case, let me give you some statistics. After minimization and determinization, the transducer has around 28 million states, similar size of transitions. This is for the full song transducer, the one that forces you to go through the whole song. Okay, the one that would not match in a snippet. It would only match whole songs. And this is the surprising thing. When you transform this transducer that only allows full songs into a factor transducer, when you think about it, it has a lot of extra, it allows way more things, right? Because it allows any possible substring. Surprisingly, it's just a little bit bigger in terms of states, even in the number of transistors. It's not that much bigger. In general, 2 times. To me, this is unexpected, because if you do naive, back of the envelope computation, you look at it. Okay, every song has an average of 1,700 phonemes. I have 15,000 songs, so in theory, the number of possible factors should be humongous, right? But not all of them happen, because there is a grammar of possible sequences that make sense, that allow. That actually restricts the problem a lot. Okay, so the next part was experiments. So we started with around 15,000 songs, MP3 format, and the things you want to experiment first is detection. What is the percentage of songs you can detect? How short you can go in the snippet? Can I go into 3 seconds, 5 seconds? What happens if I add a little bit of noise in the snippet? What happens if, for example, I play the song a little bit faster or a little bit slower? These are the kind of things you want to test in fingerprinting systems. Yes?
The number of song phonemes, does that depend upon the k-means clustering, the value of k?
Yeah.
Okay.
Yeah.
So what is the typical value of k?
I think most of this is with 1,024, I think. But I think we also play with 512, 2,000. So the typical snippet we look at, so in the database is around 1,000 hours of audio. It's pretty big, although not production quality. I mean, you would need orders of magnitude more. We experimented with 10-second snippets of 10 seconds. We also experimented with much shorter. I think we went down to 5 seconds. And these are some of the numbers. So the first thing we did was, okay, let's look at the full song transducer, okay, the one that doesn't give me the possibility of matching factors, substrings. And let's present the whole song. It should work, and indeed it works. 99.7% accuracy. Maybe it's one song out of 15,000 that fails. The second thing was, okay, now let's transform this song transducer through this sequence of steps I told you, where you first make every state and a start state, a possible state, then you transform the transducer into an automaton, you convert the output label into a number, minimize, determinize. And with 10 seconds, this is surprising, the detection is still pretty good. It's 99.5. So maybe you make, very few songs make a mistake. And of course, you experiment, because this is a speech recognition problem, you are actually doing search. We are using the same speech recognition infrastructure that we use in the speech. It's just that instead of loading a CLG grammar, we are loading our sound transducer. So this is kind of the beauty of this approach, that you can use all your speech recognition infrastructure to do music identification. And the whole system is pretty fast because we have the advantage that the query that is presented, this music snippet, is relatively clean and it has to match. This is still an identification problem. The next problem in this kind of applications you want to look at is detection. And here the idea is that not all the snippets I'm going to give you are part of the collection. It could be, a song you haven't seen before. So here the idea is that you need to actually classify whether this matches or not. So what we did is, it's a very simple approach. We first construct a universal background model by clustering all these music phonemes into a big fat music phoneme. So we score the snippet against this background model. And we're going to extract some features from this background model to build feature vectors for an SVM classifier. So what we do is a very simple feature vector. We get the log likelihood of the best path of what the recognition with the factor graph tell us. Also the score from the background model and their difference, something brain dead. I mean, it's very simple. And then you train an SVM with positive examples and with negative examples, and then you start playing, decoding and scoring against the SVM. So I think the experiments come later. We also experimented for detection with several noise and distortions. We added white noise. We experimented at different signal-to-noise ratios. We speeded up and slowed down the audio a little bit. We experimented with different encodings. What happens if my collection is encoded at 256 kilobits per second, and the snippets are, 64 kilobits per second, where you can perceive the difference. What effect does it have? So here are some tables of results. For identification, so you have two columns, identification and detection. And detection, remember, the idea is that you might have a snippet that is not part of the collection. So you want to tell me whether it's part of the collection or not only what the snippet it is. So the numbers are, obviously things work better for identification, but the degradation when you go to detection is not that bad. For noise, seems to tolerate as it is up to 44. When you go to 24, identification fails miserably, but detection doesn't, which is interesting. Speeding up, as long as it is below 2%, is reasonable. When you go to 10%, of course, things are worse. And re-encoding the MP3 snippet at lower bit rates, like 64 or 32, it also has an effect, but it's not that bad. So it's kind of interesting. This thing sort of works. Yes?
This is the same single-stage models.
Yeah. So something we did try to use similar data sets to the ones used with fingerprinting approaches, these hash map approaches. And in general, this is competitive. So and there are some things you can actually do to deal with the noise, which I think are better using a Gaussian mixture model acoustic modeling than the other approaches where they just do hash maps of spectral features. The fact that you're using Gaussian mixture models probably allows you to handle noise a little bit better. There's a lot of techniques for noise compensation that could be applied here. Again, borrowing techniques from speech recognition. We did not experiment too much with those. I think also the fact that you're using an HMM gives you a little bit more flexibility in dealing with speed ups and slowdowns than a fingerprinting approach. So anyway, so this is the main story I wanted to tell you. I think in the last 2 years, we have looked at a couple of issues. One, we wanted to see, this is mostly Meriar and Eugene, some theoretical limits of, we experimentally saw that the transducer, the factor transducer is only 2 times bigger than the sound transducer. And there has been some work to prove theoretical bounds that this is not just experimental. You can theoretically prove that at worst it's going to be 2 times. That has been published in a couple of transducer conferences, CIA I think it's called. And then another interesting piece of work, which I will not describe here, has been around the problem of building the factor transducer. When you go from the song transducer, the one that only matches songs, to the final one that matches any substring, you still go through a little bit of an explosion of states, because when you determinize and minimize, you have these problems. So there is some work that Eugene did exploring if there is a better way of building the determinize and minimize transducer faster without this memory explosion. So again, I think this has been published in another string automata conference this year. And again, they have something that is significantly faster and without the memory explosion. What I wanted to tell you, which I think is cute, is, let me go through this. When you start looking at the, okay, this is kind of interesting. You might wonder, why is this working? And if you think about it, the reason this is working is that when you look at this collection of songs, and you look, let's say a snippet of 10 seconds of audio corresponds to around 20 to 30 music phonemes. When I look at all the possible engrams of length 20 in this collection of 15,000 songs, what you actually notice is that immediately, the moment you go to 20 or so, there are very, very few repetitions. These factors of length, these substrings of length 20 or more, they happen once, twice, 3 times in the whole collection. So this is what really makes this whole thing work. The fact that when you go to 10 seconds, there is almost no repetition. And this is surprising, at least to me. This is what makes this thing work. These plots basically show you the suffix length, and the suffix would be from any point in the song to the end, and the one in the right is the factors, starting anywhere, ending anywhere within a song at different lengths, and how many you have. What you see is that after it rapidly goes down, and when you hit 20, there are very, very few. And when you hit 40, there is 1. Yes?
So you use the selection of the signal from the song, a contiguous one, or you're, I mean, in other words, you sample for 10 seconds, you know.
Anywhere. So in reality, I think I know what you're hitting at. The sequence of states induces some sort of segmentation.
Yeah.
But again, that's the beauty of having Gaussian mixtures versus fingerprints, versus spectral features in a hash map. You basically rely on the Gaussian mixture to, at the beginning not kick very well, but then in the search space, the other parts immediately kick enough to actually take you through the correct path. Yeah, so that's built-in flexibility because we use Gaussian mixtures. So, and I think that's the story I wanted to tell you. And I think Eugene is graduating this year. If you want details, I suggest you look at his thesis. Everything is there. More questions?
Have you tried to use different features than MFCC? Because MFCC seems to work well with speech, maybe because it's quasi-stationary or something like that. But
right.
I'm not sure about audio.
So I think for music, it's true that there's a lot of smoothing going on with MFCCs, definitely. But it works. I think the reason this works is not so much the spectral. Unlike traditional approaches that rely on spectral features, and they look at the spectral peaks very carefully, the reason this works is not so much the spectral features, but the temporal structure is what you can see here. The fact that when you look at substreams of length 20 or so, they are unique. So it's the temporal structure, the sequence of symbols, what matters. not so much the feature, one way or the other. Yes?
Do you think that this would be an issue if somebody's, say, querying this database by humming a tune?
Probably not, because
then whatever unit you extract from that is going to be very different from the units you're extracting from.
yeah, I think the problem you're going to have is that the features don't match, right? This is working for two reasons. What you are presenting me is a subset of my collection, so there is a very good match, modulo noise or different effects because of coding, and second, again, the uniqueness of factors. To do this, I mean, this is interesting. You can think of how to use all this infrastructure in a continuum, right? You can start with a speech recognition where the transducer encoding the grammar and the acoustics and everything is pretty lax. It allows a lot of things. This is recognition. The next thing you could do, something in the middle, is indexing, right? Where you have a collection of audio. You represent your collection of audio. It could be TV with lattices, and from these lattices you you combine them into a big transducer. From that transducer you turn it into a factor graph, and now when I give you a query, I can search. And there has been a lot of work. Meria and others rightly have done this. Okay, so this is not a speech recognition. It's search within this big graph which encodes lattices. And then you have the third stream, which is fingerprinting. You're just telling me whether you saw this subset of an audio collection. So it's a continuum. That's the way I look at it. Yes?
So where is the application here? I can guess, but...
Well, so one application could be copyright infringement, right? So a bunch of recording companies give me their music collections. I build one system like this. And when somebody submits a video to YouTube with a soundtrack that is copyrighted, I detect it. Yeah.
So this is not fingerprinting per se, right? Because fingerprinting means that you insert a particular signal inside.
Yeah, that's confusing. I have used this name used in confusing ways. Yeah, I think this is what you're referring. I think is called watermarking.
Fingerprinting is actually the case where you insert a different watermark for each customer. So I mean,
Yeah. Okay. Let's call it copyright infringement. I don't know. Yes.
So there are a range of other different types of music IR things that you could do, like genre detection.
Yes.
Or if you have a song by an artist that isn't in your collection, it might be useful to identify that it is a particular artist.
Yeah, this is another advantage which we didn't explore with this approach, unlike the other approaches. In addition of building a system for copyright infringement, you are actually inducing a structure because you are learning a string representation of songs. And once you have that, you can do a lot of things. You could use that to compute similarity, right? I have this song represented by a string. I have another song represented by another string. Are they similar? And maybe based on that, you can do clustering, in general. Another thing you can do, I have a song represented by strings. Do I see repetitions of substrings within the song? If so, those substrings could be the theme, like in the Beatles song. There's this jingle you remember. Typically, the theme is repeated. So you could do it for that. And you get all this for free. So that's another thing I like of this, unlike the spectral-based approaches. Yes?
Have you tried this in any other applications like speaker ID or language ID?
No. Because, again, the premise here is that you are giving me a subset of a song I have seen before. So it's almost the same. It's just that maybe it has a little bit of noise, but those applications are different, right? Yeah.
Have you done any work, or can you talk about it if you have done, on how to prove the system? In other words, introduce things that are not audible, but they would create symbols for you so that you never detect the song.
Oh, you mean ways to cheat the system?
You slow down. So you slow it down, maybe you lose it.
Yeah.
Aside from the slowdown.
Yeah, I mean, these systems, of course, all these fingerprinting, whatever you want to call them, systems can be defeated. In the case, the traditional systems, yeah, people, if you introduce a high pitch, if you play faster, but of course, if you introduce a high pitch, it's annoying. So if you play it faster, you saw how you can defeat it. I think, however, that because we have an HMM structure, we could possibly do something with faster. We haven't explored it, but you could possibly allow extra transitions. Although the trick is that you need to preserve the weight that indicates the song ID. But I think it's possible. You could try things like that. I don't know what effect it would have in the transducer when you determinize and minimize. It might change the problem a little bit, but yeah. Yes?
Have you tried defining different phone sets for the vocal part and the music part?
No.
So basically you can like segment and then add it to your FSM, like then it has to follow both the vocals and the...
Yes. If you listen to the music fonts, it's kind of interesting. I don't have examples, but you know they're consistent units. You have percussion, a little bit of guitar, so they seem to be consistent. I mean, when you get the same segmentation, I mean the segmentation for a music font across different songs, the system is doing the right thing. They're consistent.
Even with different vocals in it, right?
Yeah.
Okay.
Yeah. Yes.
Say more about the phones that are discovered. So you said that there's a little bit of guitar percussion. So those sound like what you're getting are basically short sequences.
Yes.
So are they typically quarter of a second, an eighth of a second?
So I think 10 seconds. I think 10 seconds correspond to 45 units. So you can do the math. They're short. In average, they're short.
Could you use a system like this to do instrument detection or compression, or could you use the phone database to start segmenting out? These are phones that are typically percussive. These are phones that are following the guitar.
I guess you could, but it would be painful, right?
Okay.
You would need label data somehow to map from music phone to instrument, but I guess you could. I mean, you could just, once you have learned the phonemes, you could present the system with songs, or guitar or whatever. Yeah, again, another reason I like this is because you can do all these things because now you have temporal structure encoded, which you cannot do with the other systems. So, but it has to be done.
Phone set sizes, right? Starting
yes.
all the way with 64 phones, all the way up to...
Yeah, so you of course, I mean, you have two things here, right? The smaller your phone set, the harder it is to disambiguate with only 40 symbols, right? Because you don't have enough possibilities. It also has the problem that there's more confusability, right? So we just explore three numbers, 500, 1,000, 2,000. They seem to work well, all of them.
I was wondering if there was a pattern in the errors in the sense when you go down to a smaller phone set, maybe somebody, I don't know if Wes meant that, but if, for example, you found that with a smaller phone set, your confusions typically are other songs that involve the same instrument, or...
It could be, yeah.
I was wondering whether you looked into what kind of errors you make as you change your...
No, we didn't look at that.
And then the other option would be, other thing that comes to mind is if you had a 64 phone set recognizer and a 128 and a 256 and all the way on, and you could have a strategy where you first, because the FST will be smaller, right?
Definitely, yes.
So you'll do a coarse match on the first one,
and
only search those songs with the finer resolution.
Yeah. I think the danger, this is kind of surprising to me, and the surprising thing is that you are using a transducer where the weight, this number, this integer that identifies the song, from 1 to 15,000, has been spread across the transducer. Okay, I think I have an example. Because when you minimize, determinize, do weight pushing, all these things, let me see. This is a good example. So, for example, here is this one. Yeah. Here, the first in the lower transducer, the first branch, the one for Beatles, Let It Be, let's assume is weight 0 for the whole song. And you can see that, let's look, for example, at a substring of only one symbol. For example, the first one, MP72. That should have a 0 weight identifying the song, and it does, right? So to me, the thing that is amazing is that you have distributed the weight, and you have done weight pushing, because when you do weight pushing, the transducer behaves better. It's smaller. It's easier to determinize. And if you make a single mistake in decoding, it's going to give you a different weight. And still it works. I mean, 99.7. So if you break down this problem into some coarse decode and then a rescoring, I don't know. I mean, I don't have any intuition of what would happen. It's kind of weird. To me, again, it's kind of surprising that you're playing this trick of transforming a transducer into an acceptor, distributing the weight across all possible arcs, and still the thing works. It's kind of magic.
Purpose 10 seconds. If you reduce it to 5 seconds, then of course.
5 seconds is a little bit worse, but still it's in the high 98, 90 something. Yes, 5 seconds is still good enough. Yeah, at some point it breaks down, of course.
Have you done anything to experiment with the size of the songs that you're identifying? So like if you scaled up to 1.5 million.
So this work I mentioned that has been done, I just mentioned, it basically was trying to approach to answer that. Will this scale linearly? And the theoretical proof is that indeed it does. I mean, let me see, I think we have that. So here's an example of how the transducer grows with a number of songs. And you basically see a very nice linear growth. This is experimental, but the theoretical work proved that that's the case. So this is nice. Linear growth is nice. It's better than quadratic or something like that. The second part you ask is, and the other thing that was published recently is how you can produce the final transducer, minimize, determinize, without paying the penalty of this expansion. These new algorithms that, just for factor transducers, will allow you to produce it faster without paying this extra memory requirement penalty. And the other thing is that, of course, so for example, the 15,000 songs, the reduced transducer, I think it requires 700 megs. But this is a transducer that is not, I mean, it's the generic OpenFST. So for example, if you look at the ARC object, it uses a lot of things we don't need. I mean, in this case, you know it's an integer, so you probably could do it with 2 bytes. So if you hack a little bit, you can probably model a factor automata for 15,000 songs with 200 megs. And the problem can be distributed across many machines trivially. So it's a nice problem in that sense. Yes?
When you use this weighted transducer, what simmering do you operate on? I'm wondering for the pushing algorithm.
So it has, I don't know the name of that one, but it has to be one where normal addition is preserved. So I guess it's not the tropical. Right, that's for log probes.
So, like every, either every incoming or every outgoing arc, the weight has to sum to a certain, the identity of multiplication, whatever.
Yeah, so those property has to be preserved. But it preserves the accumulative weight, so.
Yes. Well, I mean, under the
I'm telling you, there is a semi-ring. I don't remember the name, but I don't think it's any. I don't think it's an exotic semi-ring. I think one of the standard ones does it.
You're probably just trying. So you probably don't get a lot of ambiguity here. So aggregating over multiple accepting paths, it doesn't really matter what you use.
Yeah.
So they probably just use many.
Yeah.
In the
example,
in the example, it looked like min because the ID of the first song was showing up.
Yes.
If you looked at a single phoneme in the small example that you were showing,
I think so. It's like
if it appeared in song 0 and 1, then you'd identify song 0. If it appeared in 1 and 2, you'd identify 1.
Yeah, I think so.
So when you add noise, is it like a complete hit or miss? Meaning, if things got corrupted enough, you get nothing, and if somehow the phoning sequence survived, you get it? Or and what happens in the presence of noise?
So I guess we just look at the macro picture, which is, at some point half of them fail, but
Right, so when you say it was 86%, it means
yes.
that on 86% of the cases you found the right song.
Yes.
And when you didn't find it, you basically found the wrong song because you had an exact match on the wrong song. That's what happened, right?
So it means you match
or
something.
You match nothing at all.
No, you match something.
You may not match at all.
That's much on
It depends. Yeah, I guess. Yeah, you use a very narrow beam or something like that. It depends. No, it depends on. I think in our case we always found a path through the. Yeah, I think so. Yeah. So that's where the detection thing comes into play, where you always score, you always go through the transducer, the factor automata, but you use these three features: the likelihood of the best path, the UVM likelihood, and the ratio, to identify whether it was within the collection or not. Yeah.
Are there some other methods for the audio indexing to compare with them?
Other methods for audio indexing?
Could you compare this with anything else?
How about Shazam? What does he use?
I think everybody, as far as I know, uses spectral hash map approaches. Yeah. So there was another system in Google, and we used similar databases. As far as we could see, our numbers were in the same ballpark as their numbers. Their system is in production, though they started earlier. But I still have hope we can get this to work.
Which was faster? Or
their system was probably faster, although I suspect their memory requirements were way bigger. Because what they do is they record every 20 milliseconds. They have to extract 40 or 50 numbers, and you need to build some hash map. That's a lot of stuff. So I still have hopes for this. Okay.